Well, thank you so much. It's so nice to be here. Thank you for inviting me and the nice introduction. Um, I really have enjoyed getting to know the university a little bit better and meeting with some students yesterday. It was a lot of fun, people doing really interesting work. So I wanted to tell you a bit about some kind of cool work that I think we've been doing at IU that's a little bit outside of the beaten path of computer vision. And so first, I thought I'd tell you a little bit of a story about why I'm interested in problems that are a little bit off the main track of computer vision. But first, I know the question that you're all wondering, which is, what is Indiana University and where is it? So I thought I'd answer that question first. So this is a map of the US. Indiana University is in the state of Indiana, which is right there in sort of the center of the country. It's about a 3-hour drive to Chicago. Indiana has two other big universities that you may have heard of. One is Purdue University, which is about 2 hours away, and one is Notre Dame University, which is about 4 hours away. And IU is in the south of the state there. Just to tell you a little bit about IU, it's one of the largest universities in the US. We have about 110,000 students, and we're really well known for our arts, our humanities. We have one of the best music schools in the country, one of the best business schools in the country. We have top programs in psychology and in chemistry and biology and so on. And that will become important in a moment. And then our school, the school that I'm part of, is inside of Indiana University. It's called the Luddy School of Informatics, Computing, and Engineering, where Jangwon got his degree. One of the things we're proud of is that we are really, really broad. So we have lots of different people, everyone from like working in like the algorithmic details of proving, theoretical theories of computing kind of stuff, to high performance computing, to also people who study like the history of computing and the societal impact of computing. We have about like 140 faculty, about 3,000 students, something like that. Now, I'm getting somewhere with the story. About 3 years ago, we celebrated our bicentennial. So we were 203 years old. We only have, 400 years to go before we're as old as your university, but still, we're a third of the way there. Every bit counts. And during this bicentennial, the university started thinking about what will the next 100 years look like? What will be the next 200 years? And one of the things that, of course, emerged as part of this conversation is how important AI is. Artificial intelligence, and I'm sure you're all here, you all think about AI probably all the time. But as part of the university's commitment to this, we have a new building, a new Luddy AI building there. That was constructed a couple of years ago, and I'm the director of this new center. Now, the reason that I tell this story is now I've been thinking about what do I want as the director of the center for IU to do in AI? Like, where does it make sense for Indiana University or any university, your university or other universities, to work in AI so we can have the most impact, especially because we, and probably you, are not Google, not Facebook, not Amazon. We don't have all of the GPUs in the world like they do. We don't have all the data that they have in the world like they do. We don't have all the people that in the world like they do. And so I think this is really important for all of us to be thinking. Where do we want to have our impact? Where can we make our impact? Okay, so I think in the space of my particular area of computer vision, I've been thinking about this. How can I have the biggest impact in this new deep learning age? What does that look like? And so I think to think about like what the future of computer vision might be, or even the future of AI might be, it's useful to think a little bit about where we've come from, okay? So I think a lot of people in the media, at least in the US, think that AI was invented last November when ChatGPT was released. But of course, that's not the way it is. In the particular field of, there's all these like very exciting advances that are making the headlines. Suddenly AI is capturing the public imagination. Suddenly computer vision is capturing the public imagination in a really exciting way. Now, it's taken a long time to get here. So people have been thinking about machines that could see for about 100 years, like in this article here from 1929, Strange Eyes That Never Sleep. And there's been like lots of exciting advances and lots of sort of false starts along the way. Maybe most notoriously, in 1958, the United States Navy held a press release where they announced that they had solved AI. AI was solved. And it actually was an article that made the New York Times, one of the country's best newspapers, and it said, the Navy today revealed an electronic computer that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. That turned out not to be true. I know it is not true because 40 years later, when I was an undergraduate student entering the field of computer vision, we were trying to solve really simple things, like teach the computer that that toy bunny is the same as that toy bunny taken in this really carefully controlled lab environment. Forget like walking, talking, and seeing and reproducing yourself. It's just really simple things like this. And then, even like 15 years ago during my PhD thesis, I was really excited that instead of using those lab images, in computer vision now we could use real images that people were really taking and uploading to Flickr and YouTube and sites like that. And so my PhD thesis, among other things, has this probabilistic graphical model for detecting objects. And you can see this is for bicycle detections, worked pretty well there. If you're suspicious that those images are particularly easy, you'd be right, because there's, of course, the second row that I reveal now of like the bicycles that the thing totally missed and the extra bicycles that it saw all over the place, right? But then, of course, as we all know, about 10 years ago, there was this resurgence of neural networks, and deep learning, basically changed everything, first in object recognition and now in basically every single corner of AI. And so this has been a really exciting advance for the community, for computer vision, for AI, machine learning in general. And you can see this in many different ways. So looking at CVPR, one of the main conferences in computer vision, this is the paper submitted to CVPR by year. You can see how quickly it's growing. And as Jangwan mentioned, I'm a program chair for CVPR 2024, and we are planning for 12,000 paper submissions because it might actually reach that. And there's a lot of excitement in this community. Among other things, computer vision used to be like this little sleepy corner of science. 10 years ago, I had to explain to everyone what computer vision was. Computer vision, we're trying to detect faces, images, whatever. Okay, now, if you look at things like the publication, prominence of publications, according to Google Scholar, this is a list of the most impactful, the most important publication venues, not just in computer science, but in all of science. CVPR is number 4, right? Right after the journal Science, right above the journal The Lancet. So suddenly computer vision has this enormous prominence and all of this excitement, all of these advances. And yet there's also, as I'm sure you know, a lot of hype in the media about all of the negative consequences and all of the possible bad ways that computer vision and AI in general can turn out. From things like autonomous cars that don't work as well as we've been promised, to things like bias in algorithms. My favorite is like this security robot that quit its job by drowning itself in a fountain in a mall because like somehow we have AI that can outplay every human who has ever lived in every single like board game that has ever existed, but the robot can't avoid an obvious fountain in a completely friendly environment, right? And then another kind of consequence of all of this excitement is that people in universities like you and me are suddenly competing with a whole bunch of other people, trying to get our papers published, trying to get attention to ourselves. And so, as you know, there are giant salaries in industry that pull people from academia. There's things like the GPU Cold War, or whatever you'd call it, where basically GPU availability is a currency in its own, because certainly at IU, I cannot train GPT-3 or GPT-4 the way that OpenAI could. It's just a reality. And so I think, all of us in the field have to think about how do we adapt to this? And I personally have been adapting in a couple of different ways. I'll show you kind of two ways quickly, and then I'll talk a little bit more about one at length. That's what I really want to tell you about today. So the first way I adapted is that I thought, you know, this is kind of interesting. These changes that are rapidly happening to the computer vision community. And I wonder if like there's other examples in the history of science where this has happened, where something like deep learning comes and then like everything is that you learned before is completely almost irrelevant because everything has changed. And of course, if you go to a conference like CVPR and you're wandering around and talking to your friends, it seems like, you know, they're all kind of concerned about this, about what's going on, but we didn't know of any sort of study of this. So during the pandemic in 2020, a friend of mine who's an ethnographer, so an ethnographer is somebody who studies societies of people. He and I were thinking, why don't we actually study the computer vision research community as a society? So why don't we like see how people are feeling about all of the changes that are going on in this field? And so we, during the pandemic, conducted this study where we had like 50 people, actually more than 50 people across the world who are working in computer vision at all ranks, from students all the way up to very senior researchers at the very top universities that you can imagine. And we had them actually write little stories about like emotionally salient things that had happened to them recently in the context of computer vision. And we went back and forth and had them edit their paper, edit their stories and so on. And what we found through the process of this was actually really kind of surprising, I thought. First of all, there was a lot of excitement. You know, people are excited about the job opportunities, the funding, the exciting advances that are being made in the field. But there was also like a lot of negative feelings, things like concern about where the community is headed. People saying things like, I entered this field of computer vision because I wanted to study the science of vision. And instead, I feel like I'm tweaking little parameters on a CNN in order to get it work better and beat somebody else's paper. And then I submit my paper and it gets rejected, right? And they talked about things like the ethical consequences of computer vision now that it's being deployed in the field that they never really thought about when they were entering the field. And then there were concerns about things like that the community is growing so quickly, it's difficult to make your mark in such a crowded field. People from underrepresented groups feeling like they weren't getting their voices heard on the global stage. And so we wrote this paper, and then I did what I think might be the most daring thing in my entire academic career, which was to submit this paper to CVPR. And it actually got in. It got relatively good reviews. It got into CVPR 2021. And so if you're curious, it's a purely qualitative paper. There's no algorithms in it. There's no results charts. There's no figures. It's just about this study that's about the computer vision community. But if you're interested in learning more about sort of the trajectory of the community and what people are thinking, I'd recommend checking out this paper. It's a pretty easy, quick, fun read. So that's one way I sort of dealt with like the changes, is to look for opportunities to actually engage in the community and sort of help direct the trajectory. That's why I'm a program chair for CVPR 2024, for example, because this is an important thing for us to think about. The second way I've adapted is by doing a lot of kind of interdisciplinary work with people in other domains where I think computer vision can have a really good impact for good. And so we've been doing a lot of work on projects related to like ecology, climate change, polar science is about understanding how the ice sheets at the poles of the Earth are changing due to changing climates and using computer vision techniques to map those. Things like a 3D reconstruction project, which is trying to help in disaster recovery for if a city is hit by a natural disaster, for example. And even things like microelectronics integrity. So trying to understand if a if a computer chip is counterfeit or defective so that it doesn't fail in a critical situation. So these are things that I hadn't really thought about before, but I found collaborators and we started working on them together because I thought, well, this could be a way that I have an impact, I can have an impact in the field. But that's actually not what I wanted to talk to you about today. What I actually want to talk to you about today is sort of a third way that I have adapted to the changing landscape of computer vision. And that is really to look for new opportunities that I think are undervalued, but that I think someday will be extremely important. And I think all of you in this room, in the department that you're in, are in a unique position because I think you're thinking that way as well in terms of the future of interfaces, the future of virtual reality, augmented reality, these kinds of things. I think very, very, very related. So about 10 years ago or so, I got very interested in wearable cameras. And the reason for this was actually because Google Glass had just unveiled, Google had just unveiled their Google Glass. And everybody, at least in the US, seemed to have a massive freak out about what was going to happen because they imagined everybody's going to have Google Glass, everyone's spying on everyone all the time, you know, can't even go to the bathroom and have privacy because there's going to be 5 Google Glasses looking at me the whole time, you know, that kind of thing. It turned out that that did not actually happen. But in the context of sort of that was one of the very first one of these devices that suddenly started to gain popularity around kind of wearable cameras. I think maybe the GoPro is the one that has been the most successful so far, but there's been other things, Snapchat and so on. Snap has their Snap Smart Spectacles and stuff. The two devices up there on the right had a concept called life logging. So the idea behind the life logging device is that you wear this little thing and it takes a picture every 30 seconds throughout your day. And then at the end of the day, you get this summary of what your day was like. When I first heard of that idea of life logging with wearable cameras, I thought, that's the stupidest idea I've ever heard of. Seriously, who is so incredibly selfish that they think that every moment of their boring life needs to be recorded? And then I tried one and I realized I'm that selfish because it was really cool. So I tried wearing one for a summer and I got all these kind of interesting pictures that I never would have taken. This one, this is my mom on the other side of the breakfast table while I was visiting. And I never would have said to her, okay, wait, stop, let me take a picture of you while you're chewing. But this is a picture that, I cherish because it's a way to remember day-to-day life or whatever. This is my pet bird, Pichu, who I play a lot with and things like that. So anyway, sort of day-to-day moments that you wouldn't have normally captured. And the other cool thing is that you kind of get this view of what it's like to live in somebody else's shoes, because you get to see moment by moment what it is that they saw, how they navigated the world. So for example, just to give an example, during the pandemic, I got very interested in cycling because it was one of the few things that we could do. And it turns out that Bloomington, where Indiana University is a beautiful cycling place. And so I just spent hours and hours and hours cycling and wearing cameras. I did a whole lot of cycling. But I don't even have to tell you about that because there's actually this record of what I was doing moment by moment. And you can actually see what it was like to be me as I went through these activities. And so, you can imagine from the consumer imaging point of view that maybe in the future, we will look back to this point and we will think about what the history of photography was. And so, it went back to the daguerreotypes of the 1830s, which were one of the first forms of photography, to the Kodak camera, which invented flexible film and brought film to the masses, to the instant camera, to digital camera, to cell phone cameras that put them in our pockets. And maybe the next step is wearable cameras, maybe. And so, you folks, I think, are really in the right field to be thinking about what that would look like, what that means. And so from the perspective of someone working in computer vision, this wearable imagery, this data from worn cameras, I think is really interesting. Among the opportunities, so it's very different from the kind of traditional computer vision video, things like from surveillance cameras that are mounted above, or from the videos that people upload to YouTube, or the photos that they upload to Facebook or Flickr. Because when they upload a video or image to Facebook or Flickr, They are not trying to show what their day-to-day life is. They are trying to brag about how great their life is to you, their friends, right? So you get this very highly biased view of what life is like. Whereas with these wearable cameras, you get these real life views that are inherently human-centric because it's a person who's experiencing these things. And I could actually even argue, if I wanted to, that no other form of computer vision actually matters other than wearable cameras. Because if you think about it, vision really depends on the observer, right? The only reason there is a thing called visible light, for example, is because humans can see that portion of the electromagnetic spectrum. That's the reason it's called visible. It's not special. It's just a bunch of photons bouncing around, but there's people and animals who can see based on it. And so vision is sort of an inherently human-centric or animal-centric thing anyway. And so it really makes sense to look at these kinds of views. And then there's a ton of applications, things like assistive devices for people with visual impairments who could use these devices to get help navigating, memory aids for people with dementia or older adults who are having trouble remembering, there's safety, security, VR, AR. Autonomous driving is kind of an interesting one because a lot of the work that we did early on wearable cameras has actually now been repurposed for autonomous driving, because if you think about it, like a car driving around the world is kind of like a person wearing a camera. It's an autonomous agent that's observing the world. And so, my students have a bunch of papers that started as wearable camera papers, but then ended up becoming autonomous driving papers. Things like projecting trajectories in self-driving car videos where both the camera is moving and the people are moving, or things like detecting anomalies that indicate that there may be about to be an accident. Their initial work was on anomalies in first-person wearable camera kind of context, and then it applied equally well to the autonomous domain. We're actually really excited to be part of a new initiative that has maybe not solved this problem, but is addressing it. So we're part of something called the Ego4D Consortium, and we released last year at CVPR this Ego4D data set, which is just a massive data set. It has some 3,000 hours of video from about 850 people who wore cameras in 9 countries over 2 years. The only way we could do this is by working with others. So this is a collaboration with something like 12 universities. There's all kinds of ground truth, all kinds of other data like eye gaze and IMU and audio and so on. And actually, there was a lot of technical challenges involved in processing all this data, but the main challenge was actually this. It was how to ensure people's privacy, how to do this in a legal and ethical way. And I could give a whole separate talk about that because it was extraordinarily complicated to make that all work. But the reward of it is that we get lots of just like everyday real world views. A lot of it is synchronized. So for example, let me show you just the top one. So here's an example of 2 people who in their everyday activity were playing music together. It's synchronized across the 2 views. The crosshairs you see are eye gaze, so we know where they were looking moment to moment basis. And we have a lot of things from social interactions. So on the bottom, here's 4 people who are playing a board game, and you get eye gaze, you get lots of kind of interactions between people manipulating objects, people yelling at each other, because this was a game that encouraged people to have arguments. And so anyway, if you're curious about this work, you can check out our paper, Ego4D Around the World in 3,000 Hours of Egocentric Video, which was a paper at CVPR last year. And it has something like 100 co-authors because this is such a big project, as you can see. Okay, but now I'm finally going to get to the thing that I actually wanted to talk about. So I think these applications of wearable imagery are very interesting in like the consumer space because of all of those things that I said, things like helping people remember their days, people assisting visual impaired people, AR, VR, that kind of thing. But we've actually been excited about it for a different reason. And that's because you can actually use cameras to observe what people are doing and help answer sort of scientific questions related to human behavior. This, by the way, is a little snippet from a magazine article that was written in The Atlantic, which is a pretty prominent magazine in 1945, by someone named Vannevar Bush. Vannevar Bush had something to do with like science policy in the US. I don't remember exactly, but he wrote this article called As We May Think, that you may have heard about. It's kind of famous because, among other things, he predicted what the world would look like in the future. And he predicted things like the internet in something that he called the Memex device. It wasn't quite right, but it was a similar kind of idea. Anyway, unrelated to that, he has this kind of cool picture in the article of this scientist who is wearing a camera on his forehead. And the idea is that he's maybe a biologist or a chemist or something, and he's doing laboratory experiments. But because he has this camera, he doesn't have to like scribble down notes in his lab notebook because it's all recorded for him. And so, you know, Vannevar saw this, like, predicted that this wearable camera thing might happen. He actually did not predict, apparently, wireless technology, because you can see he had to have a wire there, which gets kind of awkward, but whatever, you know, we give him credit for part of this. So we have not been using wearable cameras for biology or chemistry the way Vannevar suggested. We've been actually using it in a different way, and that is to understand, or try to understand, what I think might be the most complicated and probably most important system in the known universe, one of the most mysterious systems. And that system is my 3-year-old nephew. And actually all of your sisters and brothers and nephews and cousins and all kinds of people, little kids. Little kids are amazing. Little kids learn to see the world in the way that we would hope computer vision would do, but they do it much more efficiently and much more robustly. They can manipulate the world the way that we hope that robotics could someday do, and yet after 70 years, we're still not there. They can learn language in a way that maybe computers have sort of been able to do as of ChatGPT, but still they're able to do this in a robust way, and they don't require trillions of documents that they downloaded from the web in order to do it, or huge electrical substations to power their brains as they're doing this. So they are really quite amazing systems. And so I've been working with some developmental psychologists at IU, Chen Yu and Linda Smith, who have developed this sort of methodology for bringing kids and parents into their lab and putting cameras and eye gaze trackers on the kids and the parents. And so because these are now wearable cameras, you can now see kind of moment to moment what the child is seeing. So we can think about this child now as not a machine learning system, but an artificial machine learning system, because they're a real system, I don't know, something like that. They're a black box who is trying to learn language, and they're trying to see the world. And with the camera, we can actually see the training data that they are getting to be able to do this. And so, you know, Chen and Linda in developmental psychology are interested in answering kind of very low-level questions. Things like, if I want to teach you the name of this object, what's the best strategy for doing it? Like, do I wait for you to look at the object and then I say cell phone? Do I look at the object, look at you, then look at the object, say cell phone? Do I wait for both of us to look at the object, then say cell phone? Like, what's the right pattern? Because sometimes the pattern works and the kid gets it. Sometimes they don't. And so the context usually is something like they'll bring people into the lab. They'll have like these objects that are novel. So they're made up objects, they're made up names. And then the parent is supposed to try to teach the name of the object to the child. And then they can look at a fine-grained way, like what training data led up to the child being able to do that. We've been working kind of at 2 levels of collaboration with them. and I've been working on them for now my lab's been working with them for close to 10 years now. Some of the collaboration is very superficial, and it's superficial in the sense that they have a problem which we help solve. So for example, they get all of this video data from the kids. Their old solution was to pay an undergraduate student, not an undergraduate student, an army of undergraduate students to go through frame by frame by frame and draw boxes around each of the objects, right? Well, now computer vision can do that automatically. So we can help sort of develop tools for their work. And we have a bunch of papers related to this, things like hand detection and hand segmentation, things like jointly estimating hand and object pose, because parents and kids are manipulating objects, and understanding how they do that is really important for their studies. Things like understanding the gaze patterns that kids use when seeing a scene. And so we have some papers that are like predicting where in the field of view the person will be looking, where their gaze will be looking, and then we know where they were actually looking, and trying to create models that are consistent with that. And the kind of cool thing about this kind of work is that for each of these projects, we typically get 2 papers out of it. Like we get a paper, in this case in NeurIPS, about the technical part, and then we got a paper in like CogSci, Cognitive Science Conference, about the like human-centered part. But actually, so this is kind of the superficial level of collaboration, where they have like a problem, and then we are like, oh, that sounds really interesting. I think we could write a CVPR paper about that. We'll help you solve that. But there's also kind of a deeper level of collaboration that we've been doing more recently. And that's the idea that maybe we can help each other. In other words, we can help develop technology for them to understand what kids do, sure. But by understanding what kids do, we might be able to build better computer vision algorithms also. And so like the motivation behind this is that kids are just amazing visual learners and language learners. They're just amazing. At their prime, a child can learn something like several dozen new words per day. And they're very good at generalization. So for example, there's documented cases, people in developmental study, psychology study this kind of thing, where kids will have a toy fire truck, and they play with their toy fire truck. They learn that it's called toy fire truck. And then from that moment on, throughout the whole rest of their life, they can see fire trucks of every variety: cartoon fire trucks, stuffed fire trucks, upside down fire trucks of the different colors, and so on. And sure, they sometimes make mistakes, but they are able to generalize amazingly to all of this different visual variation. And they do it basically based on this one-shot learning, based on examples of playing with just this one toy. They don't have catastrophic forgetting the way neural networks do, for example. And so this is amazing. Now, how they do this is, of course, an important question. And I think the question, they probably, in their little brains, they probably do not have convolutional neural networks with dropout and A6000 GPUs and right there. Probably not. So the mechanism is different. The hardware is different. And the answers to how that part works are in developmental psychology, cognitive science, and neuroscience, and so on. We have not been looking at this. This is very interesting, but haven't been looking at that. What we've been trying to do instead is understand it more from the data point of view. What kinds of data, training data, are kids getting, and what signals in that training data allow them to do this highly efficient language learning? So there's really obvious differences between what we do in computer vision and what the kids do. Obvious difference number one: if we train a computer vision algorithm on what is a car, what the natural thing to do is to go to the internet and download, or go to ImageNet, download whatever, 1 million images of cars and feed it in to the neural network. That is not what kids do. Instead, kids learn in the context of things like toy play. So they're at home, they're playing with their little toy car. They maybe only have one or two cars that they interact with, but they get sort of a massive amount of experience with that single car. They get to see it from lots of different perspectives. They get to see it big and small. They get to like see what happens when they put other objects on top. They get to see what happens when they take it outside or put it under different lighting conditions. They get to see what happens when they throw it at their mother and stuff like that, right? They get this massive amount of experience and they get to interact with the object. So this is really, really different. There's no interaction here with the deep learning network. There's no embodiment. Also, there's the type of diversity is different, right? Here we have 1 million different images of 1 million different cars. There they get experience with only maybe a few cars, their toy car, the family car, a couple of other cars. And so and that might be really important actually, because having a lot of experience with a single instance might teach them things like the invariance. So the fact that this is the same object, it looks different under this lighting than under that lighting out there, but it's the same object. But other things that you change suddenly make it be a new object class. So I'll just talk now about maybe probably like 2 little studies that we have done that are sort of in the intersection of developmental psychology and computer vision, with this idea of helping to understand what kids do and maybe using that insight to then improve computer vision long term. And I will warn you ahead of time, there's nothing earth-shattering here. These are all initial first steps. There's no Nobel Prize winning result here. It's all a little bit intuitive, but I still think it's really cool that we can sort of do this work that connects these 2 learning systems in a unique way. So I'll start by talking about this first study. And in this first study, we brought a set of 26 children and parents, 26 child-parent pairs into the lab, and they interacted with each other in kind of this simulated home environment. And so it was just like a room that had like a nice carpet and chairs and stuff. And the kids ranged from about 15 to 24 months old, around 2 years old. And that's when important language learning and visual recognition learning is happening. And in this room, we put 24 different toys that they got to play with. And we just told them, the parents, we just told them, just play with the toys with your child like you would do at home. So there's no special instructions. And then we can look at the video data that was collected, and both parent and child are wearing the cameras, and they have eye gaze trackers. So we can see throughout this time, moment by moment, the child, the parent in the same environment, playing with the same toys together. We can see what each of them sees and what each of them is looking at. And so as you look at the data from these 2 different views, you realize that like the views have a lot of differences in them. So here I have just like cropped out for one particular object, the red football helmet, all of the examples where we see it in the child view and in the parent view. And you can see that just the properties of these are visually different. The toddler's view, the objects tend to be bigger. Yeah, it's not an earth-shaking reason for that. It's because their arms are shorter. So the objects are bigger and they like crawl around the ground, right? But that could be actually really pretty important for a learning system. And so we did some computational experiments to try to understand the differences between these 2 sets of data that the parents and the kids are getting. So you can think about this in an engineering point of view. You can think about this as something like, I said to 2 agents, Agent A and Agent B, I want you to collect training data for this classifier classifying one of these objects. And I want you to do it in an efficient way. And so, Agent A goes out and they collect some training data. Agent B goes out and they collect some training data. And then they can bring it back and I could train 2 classifiers, one on data set A and one data set on data set B, and test it on a held out test set, and then see who collected the better data, whose strategy was better for collecting training data. And so in the same kind of way, we have cameras, a camera on the parent, a camera on the child. They're both interacting with the same environments, in the same environment. And we then get two data sets, A and B, child and parent. And then we can train convolutional neural networks, some CNN, on the data from A and the data from B and test it on some other held out data set of the same objects and see which one was better for training. And it turns out that sort of no matter how you slice and dice the data, the children always seem to collect better training data for the machine than the parent, which is kind of interesting and kind of cool. It suggests, for example, that there's something just about the way that kids interact with objects that is maybe ideal or better for collecting training data for training their little internal computer vision system, because it manages to train the convolutional neural network better as well. And then, of course, we were interested in, well, why is this? What are the properties of the training data that are different? Well, as I mentioned, one is object size, which is a big difference. And so you'll see in these histograms of object size on the x-axis and proportion of frames on the y-axis that the parents tend to get smaller objects in the field of view. But that's not it. That's not all of it, because if we can control for object size, when we control for object size, we find that still the kids' training data is better than the parents. So, what are the other properties? One of them that becomes kind of obvious as you look at the data is that the kids' views of objects tend to be more diverse. So more diverse in terms of viewpoints, more diverse in terms of occlusion and so on. And so we can try to actually visualize that. This is a simple visualization where we, for one particular object, I think this is like the blue toy car or something. We cropped out all the examples in the child's view and the parent's view. And then we used some feature space and projected it into 2 dimensions using multidimensional scaling. And the scaling is the same across these two, across the children and the parents. And so the fact that so what you see is that in both the child view and the parent view, there's sort of like this central core of a lot of examples that are very similar to one another, which kind of makes sense, right? A lot of the times when I'm looking at my cell phone, I'm looking at the front, and so you get a lot of like canonical views of objects. And yet sort of the difference is that the children also get all of this kind of highly diverse sort of outliers that seem to be different perspectives than what the parents are seeing. Now, this is also not earth-shattering if you think about it, because, for example, adults have like a preference towards planar views of objects. Like your cell phone, you look at the front of it, whereas a child, is playing with their cell phone from lots of different angles, throwing it in the air and seeing what happens, including it with other objects and so on. And so they're getting more diversity in the kinds of views that they see. And so we can measure that and quantify it in different ways as well. And so kind of the interesting thing here is that, these kids are just playing with toys. That's all they're doing. They're just playing with toys, and they're actively manipulating them. And in the process of doing that, they're collecting like this training data by just sort of the natural embodied interactions with the objects. And it turns out that this way of playing with the objects creates kind of more diverse views than what the parents see. And so then we were thinking, well, okay, if there's sort of this special property of the kids' data, if it's that it's this mixture of highly similar but also highly diverse examples, could we sort of reverse engineer and create a new synthetic data set that had similar properties? And if we could do that, can we then inject those same properties into a computer vision data set and get better results compared to other computer vision algorithms? So to do this, we have this very simple model where we can imagine that a data set consists of very similar examples, and this we can define as being like a tight cluster of examples in some feature space, and very diverse examples, and these ones would be like maximally different from one another in some feature space. And then you can imagine creating synthetic training data sets where the examples are real, but the mixture of examples is sampled in different biased ways, where you put together different combinations of the number of similar and diverse examples. And so this is what we did. And this is a complicated chart, so I will focus you on just one part. I think I'll focus you on that part over there. Basically, what we did is train CNN models using different different training sets where we varied the proportion of the sampling strategy we used to create that training data set. And the x-axis is showing the number of images per class in the training data set, but you can just look at this one over here, which is 200 images per class. So what we found is that if we use just the original distribution of data that was collected by the children, sample from that distribution, we get some accuracy that's like here. If we use only highly diverse examples, we get a lower accuracy. This makes sense because probably it's important for an object a learning system to see some kind of canonical views, some kind of central canonical views in order to build up a reasonable model. If you use only highly similar examples, there's also a lower accuracy, which makes sense because if you're only seeing the same views over and over again, you don't get a sense for the diversity. But if we put these two things together, 50% similar, roughly 50% similar, 50% diverse, then we get something we get an accuracy that's very similar to the distribution that the kids actually collected. So this suggests that this is sort of a simple way of constructing a data set with the same parent properties as the kids. So then once we did that, we thought, okay, well, what if we could use the same idea and manipulate existing computer vision data sets that everybody uses to inject the same property into them? Would we actually see better accuracy there also? And so we did some very preliminary experiments where we trained on images from MS COCO, which is a very popular, famous data set in computer vision. And we tested on images from ShapeNet, which is also very well known. And then the idea was we can choose different subsets of COCO and then evaluate how well those subsets do on ShapeNet. And so I'll show you some results for this experiment here. What happened is that if we just used the original MS COCO distribution, that's the red bar here, so we get some accuracy. It's fine. But if we bias the sampling of that data set using the same bias that we observed in the children, where we systematically choose about 50% highly diverse, 50% highly similar examples to kind of match that multidimensional scaling plot that I showed before, we actually get significantly, I mean, not gigantically, not Nobel Prize winning, but significantly better accuracy than the original distribution. And so it's all very preliminary. There's a lot of caveats and so on. But I think what's really cool about this is it's an example of us looking at the kinds of data the kids collect, assuming that they have, evolved over tens of millions of years to collect really good training data, injecting similar properties into a computer vision data set, and then finding that that actually improves the accuracy. And it's kind of interesting also, in computer vision and machine learning, we typically think of our training data set as just this thing that we downloaded and now we use it to train models and try to beat somebody else's accuracy, and so we can get our paper accepted. And yet in the real world, that's actually not how it works. In the real world, your boss says, I need you to create a recognition model for something, for ketchup bottles, because we have to check whether the ketchup is fully filled in this ketchup assembly line or something. And then you have to go out and actually collect training data. And what is the right strategy for collecting training data? How do you do it most efficiently? Well, if you hired like 10 different people and had them all go out and collect training data, you'd probably get 10 different classifiers. Who has the right strategy? In a kind of similar example, you can think about these kids who are interacting with the objects, and we can actually train CNNs based on each of their training data sets individually. And what we find is that across these agents, like some of the kids are apparently really good at collecting training data. Some of the kids are losers who, for whatever reason, they collect training data that isn't as good for our CNN. And it's just interesting to think about what causes that difference and what could cause what are the implications for computer vision. I'll just talk briefly about one more thing, and then I'll wrap up here. I could talk for many hours about all the different studies that we've been doing that have kind of looked at the intersection of developmental psychology and machine learning, but I thought I would bring one to your attention, which I think is really interesting. Let's say that you are a child, and let's say that that's your mother over there, and this is what you see. This is where your gaze point is, right there, in this moment. And your mother says, Pagbo. Okay, I made up that word. Okay, but she says Pagbo. And you're the child, and you want to be cooperative. And you're like, okay, I know something here is a Pagbo, but what is it? I mean, is it the thing that she's holding? Is it the thing that I'm holding? Is it the thing she's looking at? Is that a name for her face? Because I'm looking at her face and she said Pagbo. Is it a color? Is it an adjective? Is it a verb? Is it an adverb? Like, what is it? This is called the referential uncertainty problem in developmental psychology. It's about how kids can use very weak amounts of supervision and actually be able to learn language and learn objects. And we have, of course, the same problem in computer vision. We call it weakly supervised learning or unsupervised learning, where we have very weak amounts of signal. And so we can do kind of interesting experiments, again, using the child data as a source of data and conducting computational experiments to see to what extent can a computational system learn these references. And so I'll just sort of very briefly tell you about one particular study where we had, again, parents and kids playing with objects. The parent is often talking, and the parent is often saying things that are relevant to the object because they're playing together. So they might say something like, here's a little ladybug, and then they're playing with a little stuffed ladybug. So we have that audio stream. And then what we can do is whenever we see the name of an object in the parent's speech, we can record that moment as a moment where they've labeled something in the scene. And then we can take a few frames on either direction, on either temporal direction, as the sort of training images that the child collected when they heard that label. And of course, it's all like very poorly supervised. Kids are usually looking at the wrong thing when the label is said and so on. But nevertheless, we can now do sort of computational experiments where we compare the child data with the parent data using these said references, said labels as the ground truth label examples that are given. And what we find is that when you train on the child's data, the system is actually able to learn from this very weakly supervised information. 30% accuracy is not fantastic by any means, but it's at least learning on a 24-way classification problem. It's learning something. On the parents' data, we find that not so much. It's much harder. And so, among other things, this indicates, again, this is not groundbreaking. It's because the parent is trying to communicate with the child. So the parent is talking about things the child is looking at, not necessarily things that the parent is looking at. But nevertheless, there's all kinds of other computational kinds of experiments that you can do to look at, like, if you were a child, what would be the right strategy for using this training data to work to learn in the best possible way. Okay, so I think I will start wrapping up here. I just wanted to come back to my original story. I've been thinking a lot about what we should do as AI, computer vision, machine learning kind of researchers. And I talked about some of the different ways that I've been dealing with this in exciting ways, of looking for exciting applications, of looking for something like using computer vision to help developmental psychologists, which is not something that's going to make money for Facebook or Google or Amazon anytime soon. So there's much less competition. And yet, I think it's ultimately very exciting, sort of studying what AI can teach us about human intelligence and vice versa. And that project, which just started as like this side project that we thought everyone, me wearing that camera for a month so many years ago, actually has turned into like a big initiative over time. And so there we have an initiative at IU called the Learning Machines, Brains, and Children Initiative, where developmental psychologists and cognitive scientists and computer scientists are working together and thinking about some of these issues. And so for our center at IU, my vision for it is that we're not going to do all AI, because a lot of work in AI should be done at the companies where they have all the resources in the world. But what we can do as a university, as an institution which serves the public good, not as an institution which is supposed to make money, but as one that serves the public good, we can look for things like interdisciplinary, high-impact work that focuses on human-centered AI, developing AI techniques that center the person. It's not about replacing people. It's about creating techniques that work well with people, that communicate with people, that understand people, that are societally responsible, and so on. And ultimately, I think what I've come to terms with over these last few years of thinking about this is the reason that I study AI is not to get my paper accepted into CVPR, although that can be a means to an end. It's not to get another research grant, although that's a means to the end. It's not to get another award, although those make me feel good. It's not to get a higher salary, although that lets me buy things that I want to buy. It's really because we want to make people's lives better. And I think that's really important for us all to think about. I want to develop technology that makes people's lives better. That's why I'm at IU. That's why I'm at university. That's why I study AI. So with that, I'll just say thank you so much for the opportunity to talk and for your attention. If you're curious about any of the work either in my lab or our center, there's the websites, and I'm happy to answer questions if there's time either now, or feel free to send me an email later on. Thank you so much.